Good morning, everyone. My name is Zhang. I'm an engineer working in Space Star Technology Limited Company. My specialty is information security, and my research direction is lattice-based cryptography and homomorphic encryption. I feel very privileged to present my work here. My paper gives an algorithm to improve the efficiency of the Euclidean algorithm of polynomials, and the title is a probabilistic algorithm for computation of polynomial greatest common with smaller factors. I will report my work from 4 sections: background, preliminaries, some results, and my new algorithm. First, I introduce the motivation of my work. The extended Euclidean algorithm over polynomials is an important research object in polynomial computer algebra, which is not only a mathematical problem, but also a cryptographic primitive. The remainders obtained in the process of the extended Euclidean algorithm of polynomials can be used to construct the triangular basis of a certain ideal lattice, which reduces the time complexity of computing the Hamilton norm form of a basis. Here is the concept of the ideal lattice and Hamilton norm form will be given later. However, to obtain proper remainders, we need to compute lots of greatest common divisors between two large integers, which costs too much. Thus, in this paper, we focus on the problem to get desired remainders without computing so many greatest common divisors between two large integers. We combine the subresultant algorithm with lattice theory to present a probabilistic algorithm, which outputs the desired remainders with overwhelming probability and less computation complexity than the previous Euclidean algorithm over polynomials. Next, I will show the related work. The progress of subresultant algorithm is shown in 4 steps. In 1836, Euclidean introduced the pseudo division over polynomials, which extended the polynomial Euclidean algorithm in a field to a ring. In 1967, Collins explained that the ith intermediate coefficients are approximately longer by a factor of the 1 plus the square root of 2 to I than the input coefficients. This means that if we don't control the size of the coefficients during the Euclidean algorithm, they will grow exponentially, which causes large storage and computation complexity. In 1969, Knuth presented the early subresultant algorithm and gave an elegant proof of its correctness. The subresultant algorithm can remove the factors of remainders without computing any greatest common divisors of large numbers, which leads to an easy Euclidean algorithm of polynomials. In 1971, Brown showed the variant of subresultant algorithm and gave a way to remove the small factor of each remainder. The importance of the Euclidean algorithm in the ideal lattice concludes 2 parts. In 2017, we showed the special property of the Hamilton norm form of ideal lattice. Moreover, we found the relation between the triangularization over ideal lattice and the Euclidean algorithm of polynomials. In 2020, we present an algorithm to triangularize the basis of an ideal lattice, which is often used to construct ideal lattice-based crypto systems. Using this algorithm, we can reduce the time complexity of computing Smith norm form. Thus, we tried to reduce the complexity of triangularization of n basis of ideal lattice, which is equivalent to the efficient Euclidean algorithm of polynomials. In the second part, I will show some preliminaries. First, I introduce the concept of ideal lattice. Usually, we define ideal lattice of a polynomial ring. Here, f is a monic and irreducible polynomial of degree n. Consider the coefficient embedding sigma. Then the ideal generated by Gx forms a lattice under the sigma. And we call it the ideal lattice generated by Gx. Moreover, according to the early work, the highlight polynomials form a basis of ideal lattice. When fx and gx are coprime over qx, the ideal lattice is Fourier. Next, I introduce what is empty normal form. Given a square matrix H belongs to Z to n times n, then the H is empty normal form if and only if it satisfies the following three conditions. From the definition, we can see that the HNF is actually a triangular square matrix with some divisibility relation. We need to emphasize that the definition given above is only one way to define HNF according to row or column transformation and up or lower triangularization. There are other different definitions of HNF. In lattice-based cryptography, HNF is often used as a public key because for a certain lattice, any basis of the lattice has the same HNF. Thus, it lists information of lattice basis. Lemma 1 is one of my previous work. It shows that the Hamilton form of ideal lattice has a very special structure, which can be used in many cases. Resultant is the determinant of Sylvester matrix of fx and gx, which determines whether fx and gx are coprime. If resultant of fx and gx equals to 0, fx and gx are not coprime. Otherwise, they are coprime. The case subresultant of fx and gx is the determinant of skfg, which is obtained by deleting the last two key columns and key rows of fx and gx rows respectively in the Sylvester matrix of fx and gx. Obviously, when k equals to 0, the subresultant of fx and gx is indeed resultant of fx and gx. That is, S0fg equals the Sylvester matrix of fx and gx. Then I show the Euclidean algorithm of polynomials over a field. This is a similar procedure with the Euclidean algorithm of integers, except the quotient and remainder are polynomials. Given a field, let fx and gx belongs to the polynomial field. Through our paper, we let the degree of fx is larger than the degree of gx. Then the division of fx and gx yields a unique quotient qx and remainder rx such that fx equals to qx gx plus rx. Here, the degree of gx is larger than the degree of rx. The degree of qx equals to the difference of the degree of fx and gx. The detailed procedure of the Euclidean algorithm of polynomials is presented in equation set 1. However, I need to explain that all the coefficients are in the given field, which always do not satisfy our requirement. So I give the concept of pseudo division to solve the problem, which yields a unique pseudo quotient qx and pseudo remainder rx. We should multiply LCG to delta plus 1 to the divided problem or divided polynomial. Here LCG is the leading coefficient of Gx. Delta is the difference of the degree of fx and gx. In this way, all the coefficients are in the given range. After introducing the concept of pseudo division, I can show the polynomial remainder sequence in this in the equation set 2. After iterating the pseudo division, we obtain R1x to RLx. Here, the degree of RL plus 1x is negative infinity. By the way, I mentioned that the degree of 0 is negative infinity. Then R negative 1x, R0x to RLx form a sequence called the polynomial remainder sequence, short for PRS. Here R negative 1x is fx and R0x is gx. If they also form a basis of the ideal lattice generated by gx, they are named by PPRS-OL. Here the first P means primitive and OL means of lattice. Lemma 2 gives the expressions and the degrees of CIS and TIX respectively. SIS and TIS are obtained by the extended Euclidean algorithm. From the lattice aspect, here TIS can be considered the linear combination of the bases in the ideal lattice generated by GX. Next, I give the subresultant algorithm and its improved version. In the subresultant algorithm, whose procedure is presented in equation set 3 and algorithm 1, whose gives the expressions of I and beta I. We need to emphasize that the obtained PRS is not PPRS-OL with large probability. Thus, Brown gave the improved version. He removed the small factor that prevents the PRS in subresultant algorithm being PPRS-OL and denoted the small factor as tau I. He gave a way to compute all the tau I. However, the method to choose tau I doesn't work for every tau I. Here is a remark. Although the subresultant algorithm and its improved version are different, the HI appeared in the two algorithms are the same. In this paper, we focus on the problem to choose all the tau I appropriately. In the third part, I will show some results that will be used to prove the correctness of our algorithm. Proposition 1 gives the relationship of the contents of Qx, Fx, and Gx. Here, the content of a polynomial is defined as the greatest common divisor of all the coefficients of the polynomial. Moreover, I give the exact expressions of Qx. Proposition 2 gives the expressions of leading coefficient of each TIX in the improved subresultant algorithm. In fact, the HI is related to some subresultant of fx and gx, and this is why we name the algorithm as subresultant algorithm. Then before giving next lemmas, I first present a useful algorithm of our previous work. The input is a PPRS-OL from procedure 4. The algorithm outputs the triangular basis of ideal lattice generated by GX. We need to show that the algorithm 2 is equivalent with the one in the early work. Here we use polynomial representation notation instead of the lattice representation notation. Then from lemma 3 to 5, we give a sequence of the divisibility relation and the quantitative relation between the contents or leading coefficients of Rix x and ri plus 1x. Using the result Bell, we realize that LCTI is related to tau I, which is unknown. We tried some equations and found the following equation, which is highlighted with red color. And in our experiment, the equation holds with extremely high probability. In the last part, the new algorithm will be presented in algorithm 3. In the experimental result, for the often used polynomials in ideal lattice-based cryptography, x to n plus 1 and x to n minus x minus 1 minus 1. Here n is a power of 2. We give the experimental results. For each polynomial, we sample 10,000 examples randomly with the coefficients in the range -20 to 20. The correctness is present in the table. Also, in the same platform, the time cost in our algorithm is about 1/3 of the previous best algorithm. However, the algorithm is not determinant. Thus, the further research will focus on the determinant algorithm to give the exact expression of all the tau I. Thank you.